Okay, good morning. Let's get started. Morning. How are things going? Good, huh? Do you have any questions about what we covered so far? So anecdotally, one of the things about why this course is important, right? There was a call from somebody at IBM because one of you from last year was applying for a job, and I'm not on the person's recommended list, but they just want to know what was taught and what the homework projects were and whether you guys learned threading and stuff like that, right? So I don't know how you feel about what the contents are, but I think it's very important that you pick up the contents, right? So anyway, we were looking at files, and do you have any comments about? So have you started looking at the projects? How to start the project and stuff, right? What was your impression so far? Does it sound hard or it's okay? Yeah, it's not designed to be hard, but again, I have to warn you, if you wait till the last moment, this one can be the hardest project you've ever done in this class, right? Just because things have to work together, and like in a real system, you can't just define the parameters of what you want to do. You have to work with Fuse. So if you didn't do something right for Fuse will return unimplemented error or something, which will make your programs kind of act to weird stuff, right? So continuing with the file system implementation, again, we're going from a top-down kind of approach. We looked at what files are, and then we're going down to how we allocate and stuff like that, right? So we left off with the notion of allocation. Contiguous allocation is something that we kind of learned from the memory module. Your idea is to allocate a chunk of memory together, right? And right now we'll kind of pretend like this is a good allocation scheme. And the reason why it's a good allocation scheme is because it has some notions of how the files are going to be stored, whether it's going to be stored on a hard disk or CD or one of those things, which operate a certain way, right? To give you a hint, if you think of like a CD or something, you have one read head which has to go and read whatever you want. So having something in a contiguous fashion, and if you're doing a sequential file, you tend to get good performance, right? You may have seen this when you're playing a song in a CD player. If you continue to play all the way from start to end, your CD is perfectly fine. If you try to skip and move all over the place, you'll notice a big delay from going from one track to the other track and stuff like that. So we use that. So that's kind of ingrained into us, and that's one of the reasons why you try to keep them contiguous, both when the access is sequential and the kind of medium that you're accessing tends to be like that, right? And though it's not mentioned in the textbook a lot, the future seems to be using flash memory, right? Many of you may have used flash memory all over the place. It's probably in your cell phone, it's probably in a camera and all those things. And they operate in a much different fashion than any of these. They operate where you can go right into any section where you want. So you don't have this cost of seeking, going from one sector to the other. And so the contiguous allocation may not be as important, right? So it's kind of important to realize what the hardware is and try to build something which is optimized for that. And the challenge for operating system builders are, remember the layered approach we talked about. So if you're Microsoft, you have to build this file system which can be put on a CD or hard disk or a flash. So when you do a format, you would want it to kind of figure out what the hardware is and then change the way it allocates. And that makes the code more complicated, so that's something that they have to worry about, right? If they make it really optimized for the hard disk, once they move to flash, it may or may not be as good as you want. So those are things to keep in mind when we look at the notion of contiguous allocation. So here, if you ask for a file, I give you a big contiguous section of storage. And we'll see later on that may or might not translate into exactly what you wanted because of the way the things are set up, right? Hard disks are actually made of multiple platters. So even though it's contiguous, there may still be some hidden cost. But for now, assume that contiguous is good. Having things allocated in a sequential fashion is good. And so if you do that, then all you have to do is, for a file, you have to say, you have to find the starting address, ending address, and anything between that is part of your file, right? And once for all this allocation, you have to figure out how would it perform for different kind of operations, right? So the different kind of operations for files are sequential access and random access, right? Sequential access you read from start and keep reading, and then the random access is you kind of go and read, say, byte 1, byte 1000, and so on and so forth, right? So if you do this allocation, sequential read could be good because you're kind of reading, next to each other. Random access, it's not going to affect you, but it may not be really optimized for random access, right? It's really optimized for sequential. And the notion of wasteful space, which is again the notion of a external fragmentation from memory module, right? So if you allocate two blocks together, and if there's a little bit space between them, you cannot use it for anything else because you can't put another file into that. And it also affects how much you can grow, right? So if you want to grow a file, you have to kind of predict how far it can grow, and I'll give that much space, right? So to give you a sense, this is sort of what you would do. Again, ignore this is supposed to be a disk, but disks are a little bit more complicated. We'll see as we move forward. So essentially, you want to say, for example, file count starts at 0. It's of length 2 blocks. So that's the first one, right? Which means that count can go to 4 more blocks. But if you want to make it, add 5 more blocks, then you have to figure out where to move the file F. You have to either move the file F and then allocate the space, or move this count somewhere else. So it's good in the sense that sequential access is good, but it can't really grow that much. So there's a limitation on the how big it can grow, right? So one way to optimize for this, which I don't think is in your book either. So when you have disk vendors, so there are companies like EMC, Veritas, and stuff like that. Those are storage vendors. They build this massive storage arrays and stuff, and they want high performance. So they know that having this allocation of sequential access is good for your sequential program, but they also know that there's a problem if you can't grow this stuff, right? So the way they solve that is through a concept called extents, which is essentially you create super blocks, right? So you kind of call a set of blocks into an extent, and then you allocate an extent, right? So rather than if you ask for a block, and if the extent size is, say, 100, I'll give you 100 blocks extent, right? So you'll be sequential across the extent, but when you have 2 extents, you'll have the same. You'll now have the internal fragmentation within your extent. And if you want to grow, you can have multiple extents. So you get the best of both worlds, right? It's wasteful because the internal fragmentation, you lose a whole bunch. So if I give you an extent of 100 blocks, and if your file is only 1 block, then you will waste the 99 blocks. But otherwise, you could get good performance, right? So how can you justify this to somebody? So if you're a customer and you want to buy a file system, how would I justify this to you that, so what is expected, how much do you think you'll waste? If you have a extent of size 100 blocks, on average per file, how many blocks would you waste using your typical random assumption? Yeah, you'll waste 50 blocks per file, right? Are you convinced that that's a good idea? Per file, you're going to waste 50 blocks, right?
If you don't have that many files, it would be as big a deal?
So if you don't have that many files, then you don't particularly care. Yeah, and
I guess the blocks aren't that big. Then a lot of disk space.
Blocks aren't that big. The blocks are usually set by the manufacturer, right? So blocks, you're probably stuck with it. If you have a lot of space, right, then you probably don't care, right? Which is sort of the reality now, right? How many of you were in the market for some sort of a storage disk recently? So what's your impression? I don't know if you priced it out, but a terabyte of hard disk is probably a few hundred bytes, right? So if you're buying something, these are big storage vendors. disk is not, I mean, the raw disk is not the one that you worry about, right? You can buy this for less than $100. So disk is free, so you would want to get as much performance. So one of the ways you can do is, if I can be liberal with giving the disk to other people, then that's what I worry about, right? And many of you may realize that as the disk gets fuller and fuller, your performance will get really horrible, especially the modern stuff, right? So how many of you, if you notice that if your hard disk is getting almost full, like 93% or 94%, something like that, your performance will be absolutely horrible, because all these things are assumed that disk is so free, practically cheap, that you should have big disk, right? So we kind of moved past the notion of disks are expensive, you need to kind of store them kind of thing. So this is not a bad idea, because yeah, you're going to waste something, but you're going to get good performance, and disks are cheap, just buy more disk kind of thing, right? And you'll see that in the thinking, maybe not in the book, but in the modern world, where these things are cheap. So don't worry about, if you can get better performance by tweaking it a certain way, you should do that rather than trying to get the last bytes out of the stuff. So another way of allocating stuff is through linked allocation, right? So rather than having something in a sequential fashion, I have linked allocation where in each of the blocks, you store the pointer to the next block. So for example, if you have a block, you store the pointer to the next block into the block, right? Which means that on the hard disk, you will store your metadata, which is the pointer, which you should not be giving to the end user. And you'll be storing the actual data in here. So you'll waste a few bytes in each of the blocks for storing these things. And it's a very simple concept, because as for a linked list structure, all you need to know is the head of the linked list, and then you can kind of traverse it to find the rest of the contents. It doesn't waste anything. I think we have a illustration. So for the file Jeep, all you have to store is the first block. And the first block, which happens to be block number 9, will have the address for the next block, and which has a block to the next block, and so on and so forth. So if you chase these pointers, essentially you find all the blocks for the file, right? In the logical sense, the user's file happens to be in block 9, 16, 1, 2, and this is the last block, right? That's the logical view you want, but on the physical storage, it's kind of stored like this, right? So you just chase these things down, so you don't have to worry about wasting anything, because everything, as long as there's a pointer to it, you're fine, right? What would this do for sequential access? If you're reading from start to end, what would this entail? You'll have to read the first block, right? And then you know where the next block is. So till you read 9, you have no idea where the next one is. But once you read 9, you kind of know where the next block is, and so on and so forth. So sequential may or may not be too bad, depending on hardware parameters, which I haven't really talked about. But in terms of, if you want to read, you have read the current block, so you know where the next block is, and so on, right? How would you do random access? How would you figure out, let's say I want to access something which happens to be on byte 1000, right? Which, let's say, it happens to be on block 2. How would I read the block 2 for this file? I open the directory structure, I find out what the first block is, right? From that, how would I know where the second block for the file is?
Read through and see where it says the next one is, and then
Yeah, you have to read through, right? So you have to read the first block, which tells you what the next block is, the next block, and so on and so forth, right? So if you're doing random access, this is going to be really bad, because now you have to read through all the stuff. So you have to read all these things, which will kill you. And depending on the particular hardware, this may be really bad because of the way the things are set up. Even though sequentially you can read and find out where the next block is. And if you think of like a CD kind of medium where things are rotating, randomly going around like this would be a bad thing, right? But it's not wasteful, so it has its own place. It has its own place in the kind of hybrid in the FAT file system, which is the DOS file system. So what they do is they have a notion of a file allocation table and the actual data, right? Allocation table tells you where the files are. So what happens is in the allocation file, every address, every block has entry which points to the next block which is allocated to the file, right? So for example, in this table, entry 217 has an entry called 618, which means that this file, the file that you're accessing, the first block is 217, the next block is 618, the third block is 339, and that's it, right? That's where the thing ends, right? So rather than storing these pointers into the data blocks, you have a separate file allocation table block, right? So you have a separate direct table structure, and in that you keep this allocation, right? So if you want to have a new file, all you have to know is the first entry, and then you can kind of chase this to figure out where the files are, right? And the nice thing about this is, if you can keep this in memory, if you can keep this in your cache, then you don't have to, I mean, random access is not that bad, right? So if you have the whole thing in cache, you're pointing, you're chasing pointers in memory, which is not that bad. So this is a good way to get sort of good performance and a linked allocation, right? What is can you think of a bad thing with this kind of a data structure? Which you may have felt it when you ran scan disk. You may have seen the effects of this when you ran scan disk, right? Some of you mentioned that you ran scan disk on DOS machines. Yeah.
If one gets messed up, then it would mess up the whole file completely, and you wouldn't be able to get any of this.
Yeah, if one of the pointers gets messed up, right? If one of the pointers was wrong, then you have no way of finding out where the blocks are. For example, if the entry 217, instead of 618, if you wrote 0 into it, right? That means even though 618 knows from here it has to go here, nothing is actually pointing into 618, right? So now you have this little fragment, right? In this illustration, if I corrupt that one, so now I have this little fragment where there's a file which I don't know who it belongs to, but I know it has two blocks, 618 pointing to 339, right? And that means I have two blocks which I don't know who it belongs to. I can know it belongs to a certain file by making sure that if I'm not using some entry, I always write -1 or 0 or something, right? So if I were to go through the block, if I were to go through this, the file allocation table, and I find some blocks which have pointers going somewhere, but nothing pointing inside of them, that means this file belongs to somebody who I don't know what it is, but it's been allocated to somebody, right? And essentially what ScanDisk does is it puts them into a file. It'll call it ScanDisk 00 dot, I forget what the extension is. So essentially you get it run into a condition where you have some blocks which you know it belongs to a file, but you have no idea what file it belongs to, because the only way you know that is you know the start address. So if you can't chase it from there, you're kind of running into a problem, right? And that brings up issues that you have to deal with throughout the file system. This is one case that fat file systems have failure, but even in other ones, if you corrupt something on disk, then it's very hard for you to recover where it belongs to. You may be able to recover the data, you may be able to see that it belongs to a file, but you have no way of knowing what file it belongs to because of the way things are arranged, right? So that means you need to make sure that whatever you write has to be on the disk. If it's not on the disk, then bad things can happen. And in the modern machines, it becomes even harder and harder because there are multiple caches that some of them that operating system has control over, some of them the OS does not have control over. If you buy a hard disk, some of you who tried to buy the hard disks have their own little cache, right? They have like 8 megs or 16 megs or what have you. So even though you think you're writing something into the hard disk, that cache may be caching something. So if you ever try to pull the power up from your laptop, right, you'll run into a problem where you think you wrote something, but it's not returned in because of all these issues. And we'll look at the notion of log structured file systems, which try to address some of these issues. But any of these things, if you don't have this consistent data structure, then some of the files just vanish, right? Even though the file is on the disk, even though you can access those blocks, but you have no way of knowing where they are because the direct entry is not fully set up. So that's the notion of the fat file system. The problem with the fat file system, the other problem is you need to store this large the file allocation table, right? When you have a little small file, it's not a big concern. But if you have a really big file, if you have like 4 or some other really big file, then your file allocation table will have to be correspondingly big, and maintaining that in memory is fairly complicated. To give you a sense of how easy it is to create files, right? One of you in the class project for the pin traces, they collected a 32 gig pin trace file, right? Which I don't think they actually meant to run a 32 gig file. 30 gig is a fairly big one, so I'm sure if it ran through your simulator, it'll take you a long time. They just created a file and then they stored it, and I think they left it like that. And of course, you're running out of storage because machine doesn't have enough space. So if you want to create a 32 gig file, right, in a fat thing, you need to have sufficiently large table with all these pointers and stuff. So it's not a good way to go, right? Another way to allocate storage is through an index block, right? Index block basically, rather than chasing these pointers, you essentially have a table which points to the blocks directly, right? So rather than going through the table, so if I want to find block 3, I just find out block 3 and find out where the block is pointing to, right? So that's the notion of an index block, and of course we'll have to modify it a little bit because the way we have it right now, this block would be as big, this table would be as big as how big this thing should be, right? Does this bring memories of something that we looked at where there's a table here pointing to stuff on the other side? It should look like a page table, right? It's sort of like a page table because remember this is like a logical memory concept. You still have the physical addresses and the logical the translation stuff, which is the page table, which is sort of how these things work. So if you were to do this as an index block, you'll have to have one block which has the pointers to all the stuff. So when you want to read a file, you first have to read the directory entry to find out where the index is, read the index, and then you know where the different objects are. You can do sequential access or random access once you have this particular table. And depending on how big the file is, this table can be pretty long, and you read those stuff, right? But again, you don't want to do that because this table can be fairly large for modern files. So what you do is, so anyway, so this again for the traditional one we looked at. So for small files, the index could be fairly small, but if you have a large file, you have a lot of sequence. So the way you solve that is through a hierarchy, right? Sort of like what we did for the paging too. So you have a hierarchy of indexes. So we can say the first, from 0 to 1000 would be on the first entry, 1000 to 2000 in the next entry, and so on and so forth. So you have index tables of tables to get to the content. So now you first have to figure out what's outer index, read that to figure out where the inner index is, and then go from there, right? This sort of made sense in the paging infrastructure because hardware is supposed to provide this. It's all in main memory. So even though things were slower, they were not as bad as what it can be here, because the disk or the storage medium can be tens of thousands of times slower than what you expect in main memory. So the more things you have to read, the slower it gets, right? So in this model, regardless of what you're reading, you still have to read that block. You have to read that level, and this level, right? To read the block 1, I have to read the outer index, and then I have to read this table, then this one, which means that even for a small file, I still have to first read the directory entry, and then I have to read this entry, I have to read this entry, then I have to read the contents, right? So even a small file would require all this reads. Does that make sense? Even a file which is extremely small, even a file which is only 1 byte long, I still have to read the directory entry, I still have to read the outer index, then this index to find out what the content is, which may be okay or whatever. So one of the things that file system developers tend to do is they understand that things are slow. They want to kind of speed it up for the normal case, and they have no idea. So they don't really care about abnormal cases, right? So what they do is they do studies on what people typically do with files, how long the files are open, what the file size and everything. There was one of the best work done at UC Berkeley in mid-80s, like 80, 85 or 86, something like that. They looked at the files that were accessed in Berkeley Computer Science Department back then, and they had some findings which still permeate some of the decisions that they do about file systems now, right? One of the things I found was most files were small. They found that most files don't live that long. They found that most files are not shared, right, between two users. And so the notion that most files are small, right, and most directories didn't have too many files. How many of you believe this notion that most files are small? Have you ever looked at what kind of files you have in your system? What kind of files do you see in your machine? You see stuff like your PowerPoint and like stuff that you create, right? Other stuff in your system, right? Like your DLL directories and stuff. How big are they typically? Not exactly, but like, kilobytes, megabytes, gigabytes kind of thing, right? Pretty tiny, right? There are a lot of little files. Some of the stuff that they found still appears to be true, right? But to me, it's not clear whether it's a chicken and egg problem, right? Because those studies found that there are a lot of small files, which meant that a lot of the file systems are optimized for small files, which means that if you want to create big files, then you're kind of fighting against the model, right? But there's ongoing stuff. All these companies try to look at what the files are to try to optimize those. So one of the things they found was, like I said, all the files are small. So if the files are small, they found that most files are small, but there are some files which are very big, right? So you want the facility to be able to store large files and be optimal for small files. You want to do both. You want the small to be faster, but still be able to access large files. And this is a good way to go about it for large files, because essentially you can create more and more levels to make this as big as possible, right? So the more levels you have, you can access big files. But also means that if you're trying to access a small file, you pay the cost regardless of what, right? The compromise they did was what happens in Unix, right? So they know that a lot of files are small, but they also want the ability to reach big files. The way they do that is in the directory entry, the directory inode entry for a Unix file system, right? So it has all the meta information like files and sites and all those things. For the directory entries, they have a set of direct blocks, right? Which means that they directly point to the data block, right? So the block 1, 2, and certain number of blocks get directly stuff. So when I know the directory, I know how to read the first block. So if the file is small, it'll be captured by this data structure, right? But once the file gets a little bit larger, now I have a single indirection layer, which means that this points to one layer which points to data blocks, right? So now I'm paying the cost, but only when the file gets a little bit larger, right? So for these files, I need to read the directory entry and I need to read these blocks to figure out where the contents are. And then you have a double indirect layer, which means that I go from here to another master table to another table to here. And there's also one triple indirection layer, which means that it goes from, it's not illustrated here, so there's one block here, one block here, one block here, one block here, right? Which means that if you have a really big file, then in the Unix model, right, I know exactly which file I want because I can figure out what the block number I'm looking for. If it's a pretty big number, then I may have to read the directory entry, this block entry, this block entry, this block entry to get to what I want, right? So this is a way to compromise on small files and large files. And even in large files, if you tend to read sequentially a large file, you may not notice too bad a problem because you tend to reuse the stuff. So if I read this block once, I can keep this in cache. So if you do a sequential, yes, I have to read these blocks, so I'm kind of okay. If you have a really large file and I'm doing really random reading, right? randomly if I'm going to read blocks all over the place, then in this model, you will pay a price, right? You will pay a price that if you're reading randomly, then I may have to read these different layers. I may not be able to cache them, and the performance will be bad. And it's okay because the studies show that most files are small, and there are only very few large files. And the large files tend to be read sequentially, so they're okay, right? Why would a large file, what would be going in a program that will make large files be sequentially read? Or what kind of application can you think of which will do random access on a large file? Yes?
Database?
Database is what? I said two things, right? Which one is I said is sequential, one is random access.
It would be random access if you're reading from it.
Yeah, so database would be a random access stuff, right? Database if you take a database, essentially you're trying to find stuff all over you're trying to get some data from your large database. So you tend to do random access, right? So if you do random access, would this be a good model for you to go with? You tend to have large file, you tend to do randomly, right? So in that model, it's not doing anything especially for you. I mean, it acts like a indexed file allocation, right? You may get good performance or not. So, but Unix file systems are really designed for small files. If you're getting small files, you get very good performance, right? Because if you can directly go from the direct blocks, you're good, right? And that's important for you to understand if you ever want to use this stuff. So if you want to build a database, or if you want to build some application, you would have to understand how the files are stored, because depending on how it's stored, you may get good performance or you may get horrible performance, right? And this is how Unix stores them. Again, all this depends on the number of entries that you can have here, right? What does that depend on? I didn't give an example of what this number should be, right? You want to have this and this and this because you need to be able to access large files. How big should this be? How many entries can you have on the direct blocks? What does it depend on? You have no control over those, right? I mean, those are information about the mode and owners and stuff, which is true for all files. You have really no control over these because you need this to access large files. But you have control over how many entries you can have on the direct block. How do you control that? What decides that? Actually, the answer is somewhere here on the slide. Yes.
The size of the inode block?
Yeah, size of the block, right? I say it's 4K here. So size of the inode block tells you how big this whole data structure is, right? So depending on what size these pointers are, 32-bit, 64-bit, or whatever, you allocate these things. So this is whatever is left over, right? So if you have a larger block, then you have more possibility for more direct blocks, right? But then you also have more internal fragmentation, right? So internal fragmentation means that the half the block is not used, right? So if I go with the model that most files are small, if I make the block really big, that means you're going to waste a lot more, right? If you expect most files to be 1 byte, let's say, then the bigger the block is, that means you're going to waste more, right? So again, you have to figure out what a good compromise is, right? The more you waste for, so if you make the blocks smaller, then you don't have many direct blocks, but then you suffer. So you have to come up with a compromise of what you want, right? And most machines use 4 or 8K blocks right now because memories, disk space is cheap. There's no reason for it to get smaller. But again, those are compromise. And those compromises are typically made by the operating system on your behalf, but you are free to change those. So when you're trying to, if you want to install a new operating system, some of them, if you go to advanced mode, it will ask you stuff like this. What do you want as a file block size and all those things. And you should be thinking about what kind of files you're using and how these things are to figure out what the block size should be, right? And as if for people who install these things, the tools that give this information to the normal user is pretty lacking, right? How many of you messed with this when you install some operating system? How many of you install operating system from scratch for? We have very few. None of the others have installed an operating system on a machine, which is kind of strange because Microsoft always seems to say if things go wrong, reinstall, things will be fine, right? So for the people who installed the operating system, did you mess with these stuff or did you let it choose the stuff?
I have before.
You have messed with these things. So if you try to mess with these things, the tools are not really there, right? For the rest of the people who haven't installed one of these things, if you want to install, those machines are always there. I mean, like I said, make sure that nobody else is using the machine for something else before you reinstall those things. But feel free to to install something on that machine from scratch, wipe it out, and try these things, because that's the only way you can kind of see how these things work, right? You don't want to do this on your desktop that you use for day-to-day life, but those machines are fine. So that's the notion of how to allocate, how to get the directory entries. The next notion is to figure out where to keep the free blocks, right? So to figure out which blocks are free, which blocks are used. And we ran into the same problem when we talked about memory. But here, again, the problem is I need to remember this for the next time. So I need to remember which blocks are allocated, which are not allocated for the next time. So I want to make sure that it's returned to the storage, right? So I need to maintain this data structure. It has to be stored. And again, since we operate on the block level, I have to be cognizant of the fact. I need to be aware that things are in block boundaries. So I need to come up with some mechanisms. So the first mechanism is the notion of a bit vector, right? So I have a bit for every block. And so depending on what file, how big the block is, I can look through the bits to figure out which is allocated, which is not allocated, right? So essentially, depending on how big a disk is, you create a bit vector, right? And you could use one of this for your homework project to figure out what happens. So in the disk metadata, you have to have this bit vector allocated, and every time you start up your program, you have to read whatever is on the disk. If it happens to be 1, it means it's allocated. If it happens to be 0, it's not allocated. And you go from that, right? And you can use that to figure, if you want contiguous allocation, you can go through the blocks to the bits to see if you want a contiguous 10 blocks, then you can actually look in the bit vector to see some area where you have all the 10 in sequential, and then you can allocate those. And again, so the bit vector takes space, but it's only 1 bit. So hopefully, unless you have a really large storage, the amount of storage taken by your system is not that much. The other model to do that is through a linked list, and I think there's illustration in the next one, right? So again, you keep track of the now you have a free list block, right? Which is sort of, this is like what we did for the files, right? So now you create a virtual file sort of thing where you keep pointers to all the free blocks, right? So if you want a free block, you just take the first element from the list and so on. It's kind of hard to find sequential access, right? You kind of find sequential blocks because you have to search through the entries. But you can get the next block rather easily, right? And again, you run into the same problem. If this entries ever get corrupted, then what will happen if these entries get corrupted? Yes?
Either write over something that's there or not use all your free space?
Yeah, so any of these schemes, the two things that she mentioned would happen, right? If you have a free block, some way of maintaining free blocks, if those get messed up, you can do one of two things. One, you can write into a file which has already been allocated, write into a block which has already been allocated, or you may think that a block is allocated when it's not, right? So for example, if I allocate block 25 to some application, but if I didn't set the pointers to ignore that, right? That means next time the program comes up, you'll think that block 25 is free. It might give it to another file. So two files may access the same block, right? Would they know that they're accessing the same block? How can you find out if a block is allocated to this? One block is allocated to two different files, and you are not actually trying to share it. It just happens to be shared. How would you find it? Yes?
You have to run a file system check and go over all of the pointers to blocks and then count how many times each block is referenced.
Yeah, you have to go through the tedious process of going through for every file, right? You have to make sure that you chase these pointers. So if you do a pointer allocation for linked list allocation for this, you have to read every file, you have to read every block, and you have to chase down these things. And then you have to remember which ones you went through, right? You have to do this check, and then you see that you may find that one block is allocated to two different things. And if it did show that one block is allocated to two different things, what can you do?
You could remove one of the references.
You could remove one of the references, but you don't know which one it should belong to, right? You know that two people are using it, but basically those two files are hosts, right? Because now you have part of your file which is shared by somebody else, and you see this stuff, right? Some of you may have noticed this stuff. I mean, in your it used to happen actually in the Mac in version like earlier versions, where one file can suddenly appear halfway through, may appear like a binary, like you have a file, you're looking at it, and suddenly halfway through it has something else. Your program may report this as corrupted file or something, right? So when you have file corruption, one of the ways to happen is some block which belongs to something else gets allocated to you, right? And that's a bad thing because now you lose data. I mean, I'm storing something, and suddenly whatever I thought I stored, somebody else also got hold of that block. They wrote something, so whatever I wrote is lost, right? The other case where suppose I move the pointer from here to say 26, right? But I never actually gave it to some file, right? I wanted a block. I fixed this entry, so now the system thinks that 25 is allocated to somebody. So I have a pointer going from 18 to 25. But before I give it to 25, something happens. I mean, the system crashed or something, right? What's the bad thing that can happen in that way? You have a block which the system thinks it's allocated, but no one is actually using it, right? Which means that this is kind of orphaned. I mean, this block is now nobody knows. I mean, it's kind of lost, right? Again, you can go through the file system checker kind of things to figure out to reclaim those stuff, right? But at least in the grand scheme of things, that's not a bad thing to happen, right? It means that you're wasting disk space, but at least you're not going to destroy files, right? So I would rather have all my files stay rather than worry about, I mean, I would want the system to work perfectly, but if there's going to be a failure, I wouldn't mind a failure where my files, I don't use some of the blocks rather than reusing some of the blocks, right? So that's one of the philosophies behind some of the schemes that they do to work through these things. Because as you'll realize when you work for your homework project, right? I'm not expecting you to make it bulletproof, but essentially you have to make sure that everything goes into the disk. You have to make sure everything is out of the disk, right? If you ever have any bug, your bugs live on forever, right? If you did this by software, you had a bug which wrote something wrong. Until you do something like a FSAK or scan disk or something to go through the file system, you're kind of stuck with it, right? And the larger the disk is, it may take you days and hours, and actually it may take days to go through the stuff, right? Some of you may have, if you take a big hard disk and then if you do a full scan disk, it'll take you hours and hours to do this stuff because it has to read every file, it has to read all the blocks and create this big data structure and stuff. So you don't want to do that. So you want to, so some of the things that they look at is to avoid these things. And that brings up the issue of the consistency management, which is very important on these file systems, because you can assume that your programs are always correct, which never happens. Even the file systems that they sell, they have issues. So in that sense, you want to figure out which is okay. It's sort of like what you do for traffic lights, right? You know traffic lights fail, but you want to make sure that if the traffic light fails, it blinks red all over through all the side where the things slow down. You don't want to go into a case where it's green on all the sides, right? That's, even though they both fail, one is catastrophic failure, one slows things down, that's okay, right? So the solution here is, if I want to allocate something, I first allocate it, make sure it's returned to the disk, and then I do my next process. So if the system ever crashes at this point, I have already returned to the disk that is allocated, but I never actually gave it to anybody else, so it may or may not be available in another file, which means it is wasteful, but it won't cost the kind of stuff that you worry about. And especially since most of the modern disks are fairly big, you don't really worry about it. And if you have the time and energy, you can run these scan disk and disk warriors and different programs, which will go through the system for hours and hours and make your files make a little bit more space available to you, right? Most of you probably won't run that because you probably have enough space that you don't really want to get that few megabytes and storage here and there. But that's the philosophy behind all this stuff, right? And you appreciate these things because you know, like many of you may have noticed that having a disk and waiting on a disk can be painfully slow. So you want to keep that going all the time, right? And many of you may have noticed file corruption or in terms of losing a file, right? And it's never fun because you have all the important stuff and you don't want the things to be lost, right? There are other issues that we worry about rather than the allocation of these things. The other issue is the notion of how to keep, so caching plays a big role in how these things work. The more things can be in memory, the better performance you can have, as long as you make sure that whatever is in the disk is also returned back in the right order. Caching will get you good performance, and you want to worry about that. So you have a notion of a disk cache, which is sort of kind of like the memory cache, but we'll see that they're kind of there. Essentially, these caches are something that brings the disk blocks into the memory, right? So actually, the next slide we'll see that how this is very similar to the memory stuff. Some of the different ways that you may use the caching here. One of the policies that you may use is the notion of a read ahead and forget what you just used, right? So if you're doing a sequential access, if you know that a file is being used sequentially, so that means I'm going to read block 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then close. So one of the modes that people use a file is open a file, read block 1, 2, 3, 4, 5, close the file, right? In that sense, the policy would use something like a, read ahead and forget behind, which means that when I read block 1, I will read block 2, right? Then when I use block 2, I will read block 3, and I will forget block 1, right? Which is not what you do with least recently used, which we looked at memory module, because now I'm kind of forgetting what I just read, right? I forget the most recently read because I know that you're going to read through as 1 through 5, and that's it, you're going to close the file. So I don't have to remember stuff that I just read because I'm not going to come back to it, right? So in the file system, I know that a lot of people read the file, open the file, read all the way to the end, and then close the file. So there is no point for me to try to keep on to pages that in a memory system, I have no idea what you're going to do, right? This is one of the optimization they do, and this is sort of what they learned from the other scheme. So you use these different stuff. So this looks like a paging cache, but it has this little differences because of how people use these files. And one of the other things that I'll say a little bit of that, in the study that they found there are a lot of files which are not used for a long time. They're open, something is written to it, and then somebody reads from it, and then it's gone, right? And these tend to be a lot of temporary files. So if you do a compilation, your compiler will create an assembly file, write it into a file, and then give it to the assembler. Assembler will read from the file, do something, write the object file. Next program, object linker would read the object file, do something, and write it, and so on, right? And that's how a lot of these programs, so they write all these temporary files. And those don't tend to stay for a long time. And one way to optimize for that is to use memory as a file system, right? So these are weird file systems. Anything you store in there, it won't survive a crash, but these are temporary files, and they tend to get good performance. And most systems will tend to use that, basically use the memory as a file system to get something which looks like files, but not necessarily, right? And we'll see some of this and then continue with this on the next lecture.